Hi everyone, my name is Neel P, and on behalf of my co-authors, Professor Khajepour and Professor Hashemi, I'll be presenting our work titled MPC-PF, Social Interaction Aware Trajectory Prediction of Dynamic Objects for Autonomous Driving Using Potential Fields. I will begin with motivating our work by emphasizing the need for trajectory prediction. Prediction of the overall intent of pedestrians and vehicles is critical in decision-making for autonomous vehicles. To this end, we propose MPC-PF, our trajectory prediction module, which incorporates temporal location and velocity information, as well as captures agent space and agent-agent interactions via design of a cost function that embeds design of a potential field-based proximity, tendency of objects to follow a reference path in absence of other objects, such as center lines for vehicles and constant velocity for pedestrians, and deviation of direction of current heading in case of anticipated collision or to abide with scene cues. We begin by examining the model architecture. We designed MPC-PF that incorporates temporal location and velocity information of objects via state estimation and incorporates social interactions via potential field generation using two pieces of information. The first is HD map and the second agent locations. We use this information in trajectory prediction for the first stage in trajectory generation, and then secondly in trajectory optimization to iterate over different possible trajectories. In doing so, we have designed a new potential field function modeling the cost incurred by object O due to being close to object P at a given time, shown in this figure. The potential field is a function of the position vector of objects O and P, as well as the velocity of object P and some constants. Notice that the denominator of the function represents the equation of a scaled and rotated ellipse. We also provide a link to the visualization tool that can be used to gain an intuitive understanding of each of these parameters in our paper. Next, we define the MPC-PF trajectory cost function used for trajectory generation and optimization. To illustrate the three main terms in the cost function, I will use this visual illustration on the right. Given the measured position of object O in the past time steps, we have the estimate of the velocity for object O and similarly for object P1. The blue dashed line is the reference path derived from a constant velocity rollout for pedestrians, for example, and from the center line of the HD map for vehicles. The first term in the cost function, referred to as reference deviation, constrains the prediction to be close to the expected reference path. The second term allows minimizing the abrupt changes in heading angle between time steps, while the third term in the cost function considers the possible presence of other objects via potential fields. The inequalities introduced here denote that the change in heading angle predictions between consecutive time steps must be within physical limits. We perform trajectory optimization via this cost function using a constrained nonlinear optimization method that considers convergence into local minima. To validate our approach, we tested in two scenarios, the first with an oncoming nudging vehicle and the second with multiple pedestrians at a crosswalk. Note that in both scenarios, the self-driving vehicle is the one in green. Starting with the first scenario, we have an overview video on the left and agent views on the right. We have two cars parked on the road, and we have the nudging car approaching in yellow, which is opposite to the direction of travel of the self-driving vehicle. Note that these vehicles can also be seen in the agent view. Here in the top view, our prediction is in orange, the ground truth in magenta, and the constant velocity prediction in blue. We also overlay the road boundary potential fields, lane boundary potential field, and the potential field of the parked cars. We also have the potential field overlaid for the nudging car, shown here, and the self-driving vehicle. Here is the second scenario with a car stopped at a crossing with 3 pedestrians. Note that the motion of pedestrian number 1 is the most dynamic out of these 3. The predicted trajectories can also be seen in the agent view. Once again, here is the top view where our prediction is in orange, the ground truth in magenta, and the constant velocity prediction in blue. And here are the potential fields overlaid for the crosswalks and for pedestrian 1 and 2. And the potential field for pedestrian 3 as well. We perform a model evaluation via comparison of our approach with a constant velocity-based trajectory prediction model and with MPC-PF without the heading deviation consideration, and our quantitative results show that MPC-PF performs well in both of the scenarios. Thank you for watching, and I invite you to read our paper for further details.